This one is not going to have any do nows. We're just going to jump right into it. These are word problems that have to do with differential equations. For this one, this is a punctured tire problem. You have just run over a nail. As air leaks out of your tire, the rate of change of air pressure inside the tire is directly proportionate to the pressure. Directly is going to be the key word because it means that as one increases, so does the other. So that's a good thing. Also, we're talking about the rate of change of something. So we're going to be putting a ddt of, let's say, dp dt, whatever we're going to end up calling it. Write a differential equation that states this fact. Evaluate the proportionality constant if the pressure was 35 psi and decreasing at 0.28 psi per minute at the time zero. Alrighty. And last one, solve the differential equation subject to the initial condition applied to step A. Alright, let's do this problem. So, we were saying that rate of change usually means d dt of some variable, and we were talking about the rate of change of air pressure. So that means dp dt. The rate of change of pressure dependent on time. It is directly proportionate to pressure. So as this increases, so does this. There's only a coefficient correction to worry about, which we're going to call k. So now we can actually use this differential equation to plug in some initial conditions. We know that pressure, at pressure 35 psi, to just read it. Write a differential equation that states the fact, evaluate the proportionality constant if the pressure was 35 psi and decreasing at 0.28 psi minutes at time zero. Remember, decreasing means negative. Alrighty, so for the dp, right here, where this was, we're going to plug in the negative 0.28, and whether it was a p, that's where we put in the 35 psi. So when you do this, when you solve it out, your k will equal negative 0.08, and you plug that into this original function you wrote down, and we now have our differential equation, and we can now probably solve it. It's probably the next step. Solve the differential equations subject to the initial conditions implied in step A. Alrighty. In step A, the initial condition being at time zero. So when time equals zero, we had those initial conditions. Okay. So we want to get the t's on one side, which there are no t's. So just multiply by t and divide by p to get p away. So we don't have a t here at all yet, but taking its derivative, there will be a t. And then that will become a natural log because you have 1 over p. Now, in order to solve for c, you could actually already plug stuff in. You don't really need to do this. I'm just saying it. You can do this to get p by itself, but right now your goal should be to solve what c is. But doesn't matter. This probably end up being easy anyways. But I'm just saying that because in previous videos we kind of solved for c and then we solved for the variable. But in this case, they solve for the variable first and then they solve for c. Either way works. Either way will work. So, e to both sides will cancel out the natural log right here, which leaves you with a p, and then we have an e to the negative 0.8t plus c, which you can separate into this. And then this is going to become your new constant, and then you plug in 0 for t. So pressure should be 35 when t equals 0 from the initial condition thing. So that ends up being 1, so c is going to end up giving you 35. So now our equation is p equals 35 e to the negative 0.08 t. And that will be it. This one doesn't have a AP. Oh yeah, that wasn't an AP question. I liked it when in the previous video we had AP pointing guides. Doesn't matter. Let's move on to the next one. This problem wasn't done yet. Still has a C, D, and E component to it. For C, it says sketch the graph of function shows behavior a long time after the tire is punctured. Okay, we want the end behavior of an exponential function that has a negative exponent. This is kind of what you're gonna get. And when you plug in t equals 0, you have 35, so you can have that initial condition right there. For time, we don't consider negative time typically, but if you were to go to negative, it would look something like this. I mean, I can't really show better. If you were to do it, which don't do it, but it would go up like that. Because if at the negatives, these become positives. It's really the flipped version of what a exponential function looks like. However, we're not doing this nonsense, so no negative time. No negative time allowed. All right, so that was that. What will be the pressure at 10 minutes after the tire was punctured? Just plug in 10. You end up with this, so that wasn't a hard problem at all. The car is safe to drive as long as the tire pressure is 12 psi or greater. For how long after the puncture will the car be safe to drive? Well, does time decrease it or increase the psi? And as you see in the graph, as time progresses, psi goes down, which means that you want to solve for 12, and then the time must be less than that, if that makes sense. So let's put in 12 for p, and then solve for t. So they didn't actually show it, but you're going to divide by, let me have a smaller pen. You're going to end up dividing both sides by 35, find out what that is, and then do a natural log on both sides to cancel that out. And then you're going to divide by, which is, since this is going to be less than 1, your natural log is going to be negative. Divide that by the negative, let me just write it down. So you're going to have a natural log of 12 over 35 equaling negative 0.008. And that's me even stepping a step. I stepped the whole, the step where after you divide it, you have e. But then I did mention you got a natural log both sides. And the natural log and e did cancel. And then divide both sides by negative 0.008. And you should end up with, I don't know, I have somewhat of an OCD wanting to finish stuff. Alrighty, so now you got that. Now you have your t being this, and I guess it's in minutes. I can see minutes right there. So it is in minutes, and then it got translated into hours. You pretty much just divide how many hours this gives you, and then anyways, you know how to convert this into hours and minutes. Even if you didn't, that would have been fine too. But your answer is reading the problem again. How long after the puncture will the car be safe to drive? The drive? Okay, it's safe and it's 12 psi or greater. So it should be 12 hours and 13 minutes or before. Because our psi is going to be lower than that. The car is safe to drive as long as the tire pressure is 12 psi or greater. For how long after the puncture will the car be safe to drive? Okay, the car, I got it. The function that kind of represent it got punctured. So your car got punctured between 0 and 2 hours and 13 minutes. Your car is safe to drive. Okay, I made it way too complicated than it actually was. Totally forgot it was punctured. So that was that. Let's move on to the next question. Alrighty, this is an exponential growth and decay. That's problem number 17. When a water-cooled nuclear power plant is in operation, oxygen in the water is transmitted to nitrogen 17, as this figure right here. After the reactor is shut down, the radiation from the nitrogen 17 decreases in such a way that the rate of change, okay, that's kind of important, rate of change in the radiation level is directly proportionate to the radiation level. I'm not even going to look what's already been written, but when they say that, what it means is we're going to have some kind of like ddt of something, rate of change in the radiation level, whatever you want to express that as. Over here I can see they use n, so the n dt should equal some constant and then the variable, but the variable has to be in the same level, meaning you don't put k over n, that will be inverse proportionate, directly proportionate is k times n. So the fact that n is not in the denominator makes it directly proportionate. Here's why. If n gets bigger, dn dt is bigger. If dn dt is bigger, then n is bigger. That means directly proportional. Alrighty, so, and they already have written stuff right there as well. So let's continue reading. Write a differential equation that expresses the rate of change in the radiation level in terms of radiation level. Solve this equation to find an equation that expresses the radiation level in terms of time. Okay, they want you to find n, because they don't want the rate of change anymore, they just want the radiation level. So you know the drill. We need dn and n to be in the same place, so divide n on both sides. We're going to end up getting dn divided by n times k dt. We're going to get kt plus c and a natural log of n. Didn't bother writing c's on both sides. E to both sides, e to the power on both sides, we're going to get n equaling all this good stuff. E to the c can be expressed as c or just some kind of constant, which is why it's like this. Alrighty, so we're going to get our initial condition probably. Suppose that when the reactor is first shut down, the radiation level is 3 times 10 to the 17 units. After 60 seconds, the level has dropped to 5.6 times 10 to the 13 units. Write a particular equation. Alrighty. So, and if we started with 3 times 10 to the 17, so let's plug that in. That's how much we have at time equals 0. So when you solve it out, you're going to end up getting n equaling all of this good stuff. This is what you have to always do. You have to solve for your c based on the initial condition, so you can write your function one more time, but instead of having a c, you actually have a number. That's essentially what they want, all the time. Alrighty, was I supposed to do something else? After 60 seconds, write a particular equation. Alrighty. Totally forgot we still have a k. Alrighty, so we're gonna find out what k is, because as you can see, we have two variables. We have a k and we have a t. So to find out k, we're gonna plug in this information right here. When you highlight it several times, it becomes like super green. Alrighty, so let's plug in that information. 5.6 times 10 to the 13, and then we plug in 60 seconds for time. And going through the steps, we're going to divide both sides by 10 to the 17, 3 times 10 to the 17. And then in order to cancel out the e, we're going to natural log both sides. And now we have 60k, because that's canceled. And on the left side, we have natural log of this very small number. Divide both sides by 60, and your calculator should give you negative 0.143. I kind of expected that, because the natural log has a number that's less than 1. That tends to be negative. Alright, so we have k. Now we write the equation one more time without any variables except that t. Now we're good. So to just summarize this one, this is a little bit harder than the ones we've used to. We first wrote a differential equations, and then we used the initial conditions to find out what c is. But because we did a direct proportionality thing, we ended up with a constant times a variable. That was not. That's how we start the problem. It's not that it's not great, but it ended up giving us an extra variable to deal with. But since they told us what's going to happen at 60 seconds, like another condition or particular condition, it's not initial because it happened after the 0. We were able to find that second variable. Alrighty, so let's do one more. So when I said one more, I lied. What I meant to say is we're going to finish this problem. Sketch the graph of the radiation level versus time. Okay, these are... So when you have an exponential function, they tend to look like this. They tend to start from like that and then increase like this. But when you have a negative in front of the x variable, it's just a flip function. So essentially it's going to look like this. But we don't really care what happens to all of this stuff because we don't care about time being negative. That tends to happen when time is negative. So this is kind of what you're going to end up with. So that's just the background knowledge I already have. So all you really have to do is find out what that starting point is, and when t is 0, this is when t is 0, we're going to end up getting 3 times 10 to the 17. So you can just kind of mark that. Then you follow the graph that's supposed to do. It's going to be following the x-axis. It's asymptotic to the x-axis, and we call it a day. That's all you really need. It is safe to enter the reactor compartment when the radiator level has dropped to 7 times 10 to the negative 3 units. Will it be safe to enter the reactor compartment 5 minutes after the reactor has been shut down? I mean, that's an easy problem to do. You just plug in 5 minutes, and then find out whether your numbers is bigger or smaller than this number right here. Let's see what they did. They wanted to know the time. Okay, so they did it differently than I would have done it. They pretty much plugged in this value, and then they found out when it would be safe. And then if that number is greater than 5 minutes, then no, the answer would be no. So let's see what's going to happen. So you plug in this number, and then you're going to solve for t. Divide both sides by 3 times 10 to the 17. And then you're going to end up with this on the left-hand side. Natural log both sides to get rid of the e. And then you end up with, there it is, 316.16 seconds. We're asking 5 minutes, so find out what that means, because is it safe to go 5 minutes after reactor? So you divide by 60, and you end up with this. 5 minutes and 60 seconds. The answer is no. It is not safe, because it needed at least 5 minutes and 16 seconds to reach that safe level, and you trying to go in at 5 minutes. That's a bad idea. Alrighty, so that's it. That finishes today's notes. See you guys tomorrow.